This is the screencast for section 4.2, example 8. We're going to look officially at the antiderivative. So in example 7, we worked a derivative backwards, but it's actually called something. It's called the antiderivative. A function capital F of x is an antiderivative of a function f of x if the derivative of that antiderivative is f of x. I know that sounds a little confusing, but hang on a second. For all x in the domain of f, the process of finding an antiderivative is antidifferentiation. Whew, that's a lot of syllables. Okay, so we already know f of x, f prime of x, f double prime of x. They're just throwing in, okay, the antiderivative of f of x, little f, is going to be capital F of x. So there's just another way of showing a relationship between a function and its derivative. Capital F, its derivative is little f. Little f's derivative is f prime. F prime's derivative is f double prime, etc. So let's look at example 8. Find the velocity and position. Oh, 2. Okay, find the velocity and position functions of a body falling freely from a height of 0 meters, so that's its initial position, under each of the following sets of conditions. The acceleration is 9.8 meters per second squared, and the body falls from rest. That's the initial velocity. Okay, so let's see. Acceleration, a of t, is going to be 9.8. So we can find the velocity by taking its antiderivative. That's going to be 9.8x, and then don't forget, t, and don't forget that constant that always can be there, c. So how are we going to find out what c should be? Well, we know about the initial velocity. The initial velocity was 0. So at time 0, the velocity was 0, which means c equals 0, and the velocity function is just 9.8t and then plus 0, which we don't need to write. Now if we're going to work backwards from the velocity function, v of t is 9.8t, so position is going to be its antiderivative. So I'm going to add 1 to the exponent, undoing what I did in its derivative. Now I'm going to divide by that new exponent, kind of like the inverse of taking the derivative. But then also don't forget your plus c. Well, to solve for the initial, or the c in the position function, I know the initial position was 0, so the constant was 0, and the position function was just 4.9 t squared. Now in part B, the initial position is going to stay the same, but now it says the acceleration was 9.8 meters per second squared, and the body is propelled downward with an initial velocity of 1 meter per second. So v sub 0 this time is 1. So let's start with the acceleration as we did before, and that was 9.8 meters per second. Taking its antiderivative is just going to be 9.8t plus this constant, which now we have something to work with. The constant is going to be 0 this time. We're going to plug in 0 for t and 1 for v of t. So I get that the constant is 1, and then the velocity function is going to be 9.8t plus 1. Now I know that this says that the body is propelled downward, but this distance is the distance the body falls. So its propulsion is in the same direction it's falling, so we want our initial velocity to be positive 1, not negative 1. That negative would be if it was going in the opposite way that we're measuring, but since we're all measuring downward and we're the initial velocity is downward, the 1 would be positive. So now let's look at finding the position. Taking the antiderivative of v of t is going to have t as an exponent of 2, and then I'm going to, instead of multiply that 2, I'm going to divide by 2, so 9.8 divided by 2 is that 4.9 again. Now it's plus t again, and plus c. The initial position was still 0, so the position function is 4.9 t squared plus t, and then technically plus 0. Now try problem number 43. It says on the moon, the acceleration due to gravity is 1.6 meters per second squared. So we already know that's a of t, 1.6. If a rock is dropped into a crevasse, how fast will it be going just before it hits the bottom 30 seconds later? Alright, so a of t is 1.6 and it's asking for how fast at 30 seconds. That's the velocity. So I need to find the velocity function. So I need to take the antiderivative of acceleration. Velocity then is going to be 1.6t plus c. Now I need to know the initial velocity in order to solve for c, or something about the velocity. And the problem says if a rock is dropped into a crevice, not thrown, not ejected, it is dropped. So the initial velocity is 0. So v of t is 1.6t. Now I can look at v of 30 seconds, and I can see that the rock was traveling at 48. Well, its velocity was 48 right before it hit the bottom, and that would be meters per second. Acceleration was meters per second. So velocity, we lost one of those seconds. It's just a change in meter per change in seconds. B, how far below the point of release is the bottom of the crevice? Well, how far below sounds like position to me. So I need to use the velocity equation and find position. So now the new exponent of t is going to be squared, so I'm going to take 1.6 and divide by 2, and I get 0.8, but don't forget about that plus c. Now this problem doesn't say that it was dropped, 10 feet from the surface of the crevice or 20 feet below the surface of the crevice, so we're just going to assume that its initial position was 0, or we can assume that. So I get that the position function is 0.8 t squared. Now it took 30 seconds for this rock to drop down to the bottom of the crevice, so I can find its position. It fell for those 30 seconds using my position equation. So S of 30 is 720 meters. Now part C says if instead of being released from rest, the rock is thrown into the crevice from the same point with a downward velocity of 4 meters per second, when will it hit the bottom and how fast will it be going when it does? So now we need to restart all of this process, and the initial velocity this time is going to be 4. So the acceleration is still going to be 1.6. The velocity then is going to be 1.6t plus a constant, but the initial velocity is 4, which makes the constant 4, and the velocity equation is now 1.6t plus that constant 4. Now the question is asking when will it hit the bottom, so we don't know what time to plug in to find the velocity yet. We do now know, however, that this crevice was 720 meters tall. So if I go and start with the position and find out how long it took to travel those 720 meters, I can then find the velocity. So I'm going to continue on here and find the position function. And I get that the position function is 0.8t squared plus 4t. And I know what you're thinking, do I have to show all this work when I knew the constant was 0? The answer is yes. You get a point for acknowledging that you have this constant and figuring out what it is, even if it is 0. So yes, you do have to show this work, show that you understand that constant is important. Okay, so let's find out how much time it took for the position to drop 720 meters. So I plugged 720 in for the position, and with a little bit of quadratic formula, I got 27.604 seconds so it cut off about 2.5 seconds off the time to drop down to the bottom of the crevice. And now I can take that time and plug and find what velocity the object was traveling at that 27.604 seconds. And I get that it was traveling at about 48.166 meters per second, which was slightly faster than it was traveling when it was just dropped.